So this is lecture 15 already, halfway through the semester, middle of the term. And on the review, problem 6 is to solve a system of linear equations, x plus 2y plus 3z equals 8, and 2x plus 5y plus 7z equals 14. So I didn't say, so I said use Gaussian elimination. We can do it directly or using the matrix form. Maybe I'll do it directly. So let's see, I have these two, I'll do it both ways. So I have these two equations and I want to eliminate, let's say x from the second equation. So I have a new system of equations. I'm not changing the first here. But if I take the second equation minus 2 times the first equation, what do I get? I get 2x minus 2x is 0. 5y minus 4y is y. 7z minus 6z is z. And 14 minus 16 is minus 2. So if I did this correctly, here's a system of equations, and this is the equivalent system in which I've eliminated x from the second equation. Right? I took the second equation minus 2 times the first. And okay. Then the next step is to eliminate the y term from the first equation. So my second equation is y plus z equals minus 2. And I can take the first equation minus 2 times the second. So x minus 0 is x. 2y minus 2y is 0. 3z minus 2z is z. And 8 minus minus 4 is 12. So this is an equivalent system of equations. So in this system of equations, no matter what z is, x is going to be 12 minus z, and y is going to be minus 2 minus z. So x, y, z, the solution of this system will be 12 minus z, minus 2 minus z, and z. I can think of this as 0 plus z if I like. So this is the vector 12 minus 2, 0, plus minus z, z, or 12 minus 2, 0, plus z times the vector minus 1, 0. So let me, before I go on, let me just check. Suppose I plug in 12 minus 2, 0 into the equations. My first equation becomes 12 plus 2 times minus 2 plus 3 times 0 is 12 minus 4 is 8. So that checks. And the second equation is 2 times 12 plus 5 times minus 2 plus 7 times 0. That's 24 minus 10. That's equal to 14. So that also checks. So this is a solution of the inhomogeneous system. What about this? If I let x equal minus 1 and y equal minus 1, I have a problem. So
wouldn't it be z times -1, -1, 1?
Ah, thank you. Yes. That's why we check. So I would have minus 1 minus 2 is minus 3 plus 3 is 0. Minus 2 minus 5 minus 7 plus 7 is 0. So this is a solution of the homogeneous system. So as an affine subspace, the solution space L is the vector 12 minus 2, 0, plus the subspace, which is all scalar multiples of the vector minus 1, 1. So this is using Gaussian elimination on the system of equations to get the solution. Okay. So this is one way to solve this problem. But before I go on, let me ask you if there are any questions about this.
So the solution itself was already in the form for an affine subspace, right?
So this is the form of an affine subspace, that.
But let's say we had left it how you simplified it, the line above. Would we lose points for that?
Well, but once you have here, you might as well write this. I mean, there's no reason to stop. Just one more line. So, I mean, why not write it like this?
Okay.
So this is a fixed vector plus a subspace. I mean, you can stop here, but why? Why?
I have a question.
Go ahead.
On the top, how did you simplify to y plus z equals -2?
I took, so to get from here to here, what I did was I subtracted 2 times equation 1 from equation 2. I took the second equation minus 2 times the first equation.
Thank you.
Now, the second way to do this problem, which is Gaussian elimination in matrix form, which is I have my system of equations and I write down the associated matrix. So let me write down the equations again. X plus 2y plus 3z equals 8. 2x plus 5y plus 7z equals 14. So the matrix of coefficients is 1, 2, 3, 2, 5, 7, and the right-hand side is 8, 14. So I have this matrix and I want to put it in reduced row echelon form. So I have my first line, and if I subtract 2 times the first line from the second, I get 0, 1, 1, minus 2. And then to get a 0 here, I take the first line minus 2 times the second line. First row minus twice the second row. I get 1, 0, 1, 12. And now this is in reduced row echelon form. And the corresponding system of equations is x plus z equal 12, y plus z equal minus 2. That's exactly the system of equations I had here, or here, same thing, and I go on the same way. So this is just an alternative way of doing the Gaussian elimination.
Do you think you could do number 11?
Okay. So number 11 says the following. We have W, a subspace generated by M vectors. So say it's generated by the vectors W1, W2, up to W sub M. And I take a sequence of n vectors. So I have n vectors in a sequence, V1, V2, up to V sub n. And we're told that the number of vectors n is bigger than the number of generators m. So this inequality is essential. And I want to show that the set of vectors v1 up to v sub n is linearly dependent. So that means we must show there exist scalars x1 up to xn, not all 0, such that x1 v1 plus x2 v2 up to xn vn is equal to the 0 vector. That's the definition of linear dependence. So how can we do this? The only thing we know is that all the v vectors belong to the subspace W. V sub I is in W for all I. So what does it mean to be in W? It means W is all linear combinations of the generators. So for example, V1 will be some linear combination of W1 up to W sub m. So let's say the scalars of this are A11, A21 up to AM1. So these AIJs, these scalars, are all just real numbers. So V1 is this linear combination of W1 up to Wn. V2 will be another linear combination of those same m vectors. All the way down to V sub n, A1n W1, A2n W2, AMN WM. So I've written all of these, each of these n vectors as a linear combination of the generators W. So then what is x1 v1 plus x2 v2 up to xn vn? So x1 v1 is x1 times this. And x2 v2 is x2 times this. All the way up to, you do this for each of the n vectors, the last thing you get is xn vn, which is xn times a1n plus a2n up to a mn w1, w2, wm. And now in each of these parenthesized things, I have a w1, for example. So what is the coefficient of W1? This is going to be something times W1. What is it? It's A11 X1, A12 X2, all the way up to A1N XN. And then I also have a W2 in each of these expressions. And what's the coefficient of W2? It's A21X1 plus A22.
They're mine. I just designed them a long time ago and never got around to building them.
And everyone themselves.
Up to A2N XN, all the way up to the last. Then we just do this for each of these W vectors. So what's the coefficient finally of W sub m? it's AM1x1 plus oops, AM2 x2 up to AMN xn. And again, we want to know if we can find x is not all zero, such that this is equal to 0. And this will be 0 if all of the coefficients are 0. So we try to solve the system of homogeneous equations, A11x1 plus A12x2 up to A1n xn equals 0. A21x1 plus A22x2, A2n xn equals 0. Down to finally AM1x1 plus AM2x2 plus AMN xn equals 0. We want to try and solve this system of equations. And what is this? This is a homogeneous system, because all the right-hand sides are 0. We have m equations, n variables, and m is less than n. That was the hypothesis. We have more variables than equations. And so by the big theorem, which you were asked to prove in problem 10, there is a solution in x's with some xi different from 0. So the fact that you have a non-zero solution of this system of equations means that the vectors, the v's, are linearly dependent. So problem 11 in the review sheet depends on problem 10, which was the big theorem in the lectures. That's the proof, which is exactly the proof that you'll find in the book that's posted on Blackboard for the course.
What page would the proof be on?
See if I can find it.
How many points is that problem?
This is a review sheet. A review sheet's not the exam.
I understand that, but I want to know how many points would that similar question would be on the exam.
On the exam, every question will be 10 points.
Okay,
They're all the same. So in the first chapter on linear equations, section 1.5. So section 5 is linear. The head of the section is, the title of the section is Linear Systems with More Variables Than Equations. And it's theorem 1.6. It's exactly what is, that's the theorem that we're using here. And the proof takes a couple of pages.
On the exam, will we have proofs that are like this intensive, or
No.
will it be less like difficult?
Probably less difficult. Only because it's not so much that this is difficult, it's just that there's a lot of writing down to do. And in a timed exam, you don't have that much time for all the writing, so I can't give you, I'm not going to give you problems that take pages and pages to solve.
Okay, thank you.
But there will be proofs. But that's a small part of the exam. Most of the exam will be computational problems. Plus, there will be, the exam might have 12 questions and you choose 10. So if there's a question you don't like, you can skip it and still get 100 on the exam.
Would you be able to do problem 9B?
Sorry?
Would you be able to do problem 9B?
Yes. So 9B is you have W1 and W2 subspaces of Rn, and we want to prove that the intersection is a subspace. So remember, if this is Rn, and here we have a subspace W1, and here we have a subspace W2, the intersection, it's all vectors W, such that W belongs to both of the sets. W is in W1, and W is also in W2. That's the intersection. So what is a subspace? So you have to know, what is the definition of a subspace? So a subspace, W of Rn, has to satisfy the following three properties. First, the zero vector is in the subspace. If W and W prime are in the subspace, then the sum is in the subspace. So this is closed under addition. And if W is in the subspace and C is any scalar, then C times W is in the subspace. So a subspace is a set contained in the vector space Rn that contains the zero vector and is closed under vector addition and scalar multiplication. So W1 is a subspace, so 0 is in W1, because that's part of the definition of a subspace. And W2 is a subspace, so 0 is in W2. But that means the zero vector is in both of them, it's in the intersection. So this first condition, that a subspace contains the zero vector, is satisfied. Okay. Now then we have to show the subspace is closed under vector addition, so that W be in the intersection and W2 be in the intersection. Or say W prime, W1 and W prime, or maybe, yeah. So, but if W is in the intersection, that means W is in W1 and W is in W2. And if W prime is in the intersection, that means W prime is in W1 and W prime is also in W2. But if W and W prime both belong to W1, then W plus W prime is in W1. And if the vectors W and W prime both belong to the subspace W2, then W plus W prime also belongs to W2. And it belongs to both of them. So W plus W prime is in their intersection. So this is the proof that the intersection is closed under vector addition. And similarly, if W is in W1 intersect W2, that means W is in W1. So C times W is in W1 because W1 is a subspace and is closed under vector addition. And W is in the vector space W2, so C W is also in W2. So this vector W times the scalar C belongs to both of the two subspaces. So CW is in W1 intersect W2. So this intersection of two subspaces is also closed under scalar multiplication. So that is the proof that the intersection of two subspaces is a subspace.
Can I see the whole page?
That's it.
Can you repeat the last step of the proof?
This.
Yes.
So W, take a vector in the intersection. We have to prove the intersection of two subspaces is closed under scalar multiplication. So if W is in the intersection, it belongs to both W1 and W2. Take a scalar C. C times W is in W1 because W1 is a subspace. W is in the vector subspace W2, so CW is also in W2. So this vector C times W belongs to both subspaces, therefore it belongs to their intersection. That's the definition of intersection.
All right, I understand now. Thank you.
Okay, good.
Can we just write it notationally like how you did, or
Sorry?
can we write that notationally like you did? Or do we have to write out the words saying that C is W is in a subspace, so that implies C is also in the subspace? CW is also, it's like, do we have to
No,
write the
no, you're certainly allowed to use mathematical notation.
Okay,
But when you write something, you have to say why it's true.
okay.
That is, the more you explain, the better your proof is. And you have to explain enough so I know what it is you're doing. Right. Other questions?
Can we do it? Can we do number 14?
Sure. So we want to draw the subspace. All vectors x, y in R2 such that 3x minus 2y equals 0. So 3x minus 2y equals 0 is the same as 2y equals 3x, or y equals 3/2 x. So that's just a straight line with y-intercept 0 and slope 3/2. This is the subspace. Just the line y equal 3/2 x.
So from 3x minus 2y equals 0, you just bring the negative 2y.
I just solve for y.
Okay, you solve for y. Is okay. And then can you explain how you graphed it a little bit?
Yeah. What's the graph of y equal 3/2 x? That's pre-calculus, right? Just graphing a straight line in the plane. Right? I mean, you did that in calculus, you did that in pre-calculus.
Please explain it. Like, where did you start from? Like 0? Where's the points?
So, do you know if you have a straight line, y equals mx plus b? Do you know what the graph of that looks like? That's the line where the y-intercept is b and the slope is m. So here, the y-intercept is 0. When you let x equal 0, y equals 0. When you let x equal 2, for example, y is equal to 3. This is just the line that goes through the points 0, 0, and 2, 3. That's the line with slope at 3/2.
Okay, so 2 is x, 3 is y.
Well, that's 1 point on the line, yes.
Okay, so we're
And if you have the line, I'm sorry, go ahead.
yes. So just graphing it like that, the first point that I just said, and then is there something else that we need to show you?
No, for part, that's the graph. That's,
Okay.
you drew the vector subspace, that's it.
Oh.
And in the second part where you have 3x minus 2y equals, for example, 2, again, you have to solve that equation for y. 2y is 3x minus 2. Y is 3/2 x minus 1. So that's a line with the same slope. This is minus 1. And it's this line. That's just the line y equals 3/2 x minus 1.
So in that situation, the x would be 2, the y would be 3, and then the coordinate -1.
No. I don't know what you mean by x. I mean, do you remember in calculus when you had to graph a straight line?
I mean, Professor, I'm asking you right now because I don't know.
No, I understand that, but I'm asking you, but didn't you have to do this very often in calculus?
I understand, Professor, but I haven't been doing math for 2 years. That's why I'm asking.
Right, okay, so in general, if you have the equation y equals mx plus b, this is the way you graph the line. The y-intercept, where the line crosses the y-axis, is when y is equal to b. And the slope is m. So if you go over 1, you go up m. So for example, if you have y equals 3/2 x minus 1, when x is 0, y is minus 1. Just make a little table. X, y. So when x is 0, y is -1. When x is 1, y is 3/2 minus 1, or a half. When x is 2, y is 3 minus 1, or 2. When x is 3, y is 9/2 minus 1, which is 7/2. So if you just graph all these points on the plane, when x is 0, it's -1. When x is, so this is -1, 0, 1, 2, 3, 1, 2, 3. When x is 1, y is a half. When x is 2, y is 2. When x is 3, y is 7/2. You see, all these points lie on a line. The line through those points is the graph of this equation.
Thank you.
Can you go over number 18?
So if A is the matrix A, B, C, D, then by definition, the definition of the determinant of A is AD minus BC. So suppose we have the equations AX plus BY equals R, CX plus DY equals S. And we want to prove this system has a unique solution if and only if the determinant is different from 0. So let's suppose the determinant of A, which is AD minus BC, is not 0. Then we try to solve these equations. So you solve two equations and two unknowns the way you have been doing certainly for a long time. You can eliminate the y. So you can multiply the first equation by d. You can multiply the second equation by b. You can subtract, these cancel. You get AD minus BCX equals RD minus SB. So X, and I can divide by AD minus BC because my hypothesis was this is not 0. So X is RD minus SB over AD minus BC. AD minus BC is the determinant of A. And RD minus SB, I'm told what the answer is. I'm told this is supposed to be, if I take the matrix RSBD, what is this determinant? RD minus SB. So that's equal to this. So if I solve for X, I get this. And similarly, if I solve for Y, I will get AD minus BC. I will get the determinant of ACRS. You just do the work, and this is what you find. So long as the determinant of A is not 0, and I can divide by it, I get these values for X and Y. They are unique. There's nothing else X and Y can be.
Can you explain 7b?
Before you go on, the 18, is that A and B?
Yes, because actually I proved that if the determinant of A is different from 0, these equations have this unique solution. So that's A and B together.
Can I see the previous page before this one, please? What problem was this one? 14?
Yes.
Okay, thank you. For this one, they said draw for C equals -2 and C equals 2.
Right.
Was that,
Sorry?
is this the drawing for both of them?
No. This is for 3x minus 2y equals 2. And if you want to solve 3x minus 2y equals -2, that's 2y equals 3x plus 2. Y, y is 3/2 x plus 1. So that would be the parallel line going through the point 1. So y equals 3/2 x plus 1 is this line, or 3x minus 2y equals -2. It's the red line. So when c is equal to -2, that's the red line. When c equals +2, it's the pencil line.
Okay.
Can you explain 7b?
Sorry?
Can you explain 7b?
Sure. So in problem 7, we have vectors f1 is 2, 3, f2 is 1, 2. And if we take a vector x with coordinates x1, x2, we want to show this is a unique linear combination of these two vectors. So we must compute C1 and C2 such that the vector x is C1F1 plus C2F2. Right. That's what we have to do. This is the equation written in vector form. If you write this in terms of the coordinates, x is x1, x2, and this has to be equal to C1 times F1 plus C2 times 1, 2. What is this? This is C1 times this vector is 2C1, 3C1, and C times this vector is C2, 2C2. So this is 2, 1 plus C2, 3C1 plus 2C2. In other words, if we compare coordinates, C1 and C2 have to satisfy these two equations. 2C1 plus C2 equals x1, and 3C1 plus 2C2 equals x2. So this comes down to solving these two equations and two unknowns. Now, if you look at the matrix of coefficients, 2, 1, 3, 2, that determinant is 2 times 2 minus 3 times 1 is 4 minus 3 is 1. So just the fact that the determinant is non-zero means this system of equations has a non-zero solution. And the solution is unique. So if I wanted to use this fact about two equations and two unknowns, I would be done. Otherwise, I have to solve these equations. And how do I solve these equations? So if I take the first equation and multiply it by 2, I get 4c1 plus 2c2 equals 2x1. And the second equation, 3c1 plus 2c2 equals x2. If I subtract, I get c1 is 2x1 minus x2. So c1 is determined. And from this first equation, c2 is x1 minus 2c1. So that's x1 minus 2. This is c1, 2x1 minus x2. So c2 is equal to minus 3x2 plus 2x2. So this is a very complete proof that there exists unique scalars C1 and C2 that satisfy this equation. And here they are. They're these functions of x1 and x2.
How did you get 4c1 on the left-hand side?
Here? This one? Is this what you're talking about?
Yes.
I took this equation and multiplied it by 2. 4c1 plus 2c2 equals 2x1. So I took this equation times 2, and I get this.
And what was your indicator to use to?
Excuse me?
What was your indicator to use the number 2?
Because then when I subtract that new equation, this equation from this equation, the C2s cancel, and I can solve for C1.
By the way, was that a typo in B when you said to find the vectors in find the vectors in R3?
Oh, yeah, thank you. Yeah, that should be R2.
Okay.
Can you do question 16, please?
Sure, just one sec. Okay, I'm sorry, which question?
16. 16.
Yeah, so that's exactly the problem I did a few minutes ago. A few minutes ago, we had to prove that. So if you look at problem number 9, number 9, you had to show that if W1 and W2 were subspaces, then W1 intersect W2 is a subspace. And in fact, I shouldn't have put this problem. This problem 16 is really, it just repeats problem number 9. It's exactly the same thing.
Okay, so then can you do number 12, please?
Number 12. Sure. Number 12. Number 12, just solving those equations?
Yeah.
Okay. So you have 4x minus 7y equals minus 28. So let's say we just solve for y. 7y is 4x plus 28. So y is 4/7 x plus 4. So if you have any solution xy, for any value of x, y is going to be 4 plus 4/7 x, which is like the sum of the vector 0, 4 plus x 4/7 x, which is like the vector 0, 4 plus x times the vector 1 4/7. So the solution space L is all vectors 0, 4 plus any vector which is x times 1 4/7 for x and r. All right, you're just solving that one linear equation. So the vector solution is this. Right, that's A. Right, so. So before I go on, is there a question about this? This is basically a high school algebra problem, except we're using vectors as our notational device for describing the solutions. Okay. The vectors that solve this equation are vectors of this form. Now, in part B, we have one equation in 3 variables, x plus 13y minus 7z equal 2. And you can solve for any one of those variables. I'll solve for x just because I'll avoid fractions. So x, for any values of y and z, x is going to be 2 minus 13y plus 7z, right? I just brought all this to the other side of the equation. So for any solution x, y, z, y and z can be anything, but x has to be 2 minus 13y plus 7z. So just to make this very clear in terms of how it's represented, this is 2 minus 13y plus 7z. Y is the second coordinate, and z is the third coordinate. This is like 0 plus 1 times y plus 0 times z, if you like. 0 plus 0 times y plus 1 times z. So if I write this in vector form, this is the vector 2, 0, 0 plus the vector minus 13y, y, 0 plus the vector 7z, 0, z. So this is 2, 0, 0 plus y times the vector minus 13, 1, 0 plus z times the vector 7, 0, 1. So to write the solution in vector form, this is it. It's this fixed vector plus any scalar multiple of this plus any other scalar multiple of this.
What if we leave it like you did the step before and not factor out the y and the z?
Like this?
No, towards the left hand, the right hand side, all the way right there.
That's fine. That's okay.
Okay. Can we do number 15?
Can you do C, Professor?
Okay, so let me finish this and then I'll do number 15. So so 12C, now we have an equation, one equation in 4 variables, 2x minus y minus 3z plus w equals 5. And I can solve for any one vector in terms of the other. So just to make it, to avoid fractions, I can solve for either w or y. Let me solve for y. So that's the same as saying that y, if I bring the y to the other side, y and the, well, I'll bring the w to the other side, but it really makes no difference. So w, so I'm going to bring all of this to the other side of the equation. So w equals 5 minus 2x plus y plus 3z. So whenever I have a solution x, y, z, w for this equation, x, y, and z can be anything, but once you pick x, y, and z, w must be equal to this, 5 minus 2x plus y plus 3z. And I can write this in vector form as 0, 0, 0, 5 plus x 0, 0 minus 2x plus what I have for y, 0, y, 0, y plus what I have for z, 0, 0, z, 3z. So this is the vector 0, 0, 0, 5 plus x times the vector 1, 0, 0, minus 2 plus y times the vector 0, 1, 0, 1 plus z times the vector 0, 0, 1, 3. So in vector form, every solution of this equation looks like this.
And for these, we don't have to write them in terms of like affine subspaces.
No, because I didn't ask you to. I just said write the solutions as vectors. Okay, someone had another question? Which one?
15.
Okay. So in number 15, we have a subspace W and a vector V naught in Rn. And we look at the affine subspace V naught plus W. And suppose we take X and Y in this subspace. So what does that mean? If X is in the affine subspace, X is equal to V0 plus W1, where some W1 in W, and Y is equal to V0 plus W2 for some W2 in W, right? That's what it means to be in this affine subspace. Every vector is V naught plus something in W. So I can write X and Y in this form. So what can I say about 1 minus Tx plus T times Y? That's 1 minus T. What is X? V naught plus W1. And T times Y, that's V naught plus W2. So let's just expand this. This is 1 minus T V naught plus 1 minus T W1 plus T V naught plus T W2. 1 minus T V naught is V naught minus T V naught. Plus here I have it plus T V naught. Plus 1 minus T W1 plus T W2. So minus T V naught plus T V naught, they cancel. So this is just V naught plus this. But W1 and W2 belong to the subspace W. So every linear combination does. This is just some vector W for some W in the subspace. So this is in L. So this very special sort of linear combination of two vectors in the affine subspace gives me another vector in the affine subspace.
Can you explain the
Wait,
third?
any question? Is there a question about this?
Yeah.
Go ahead.
Can you explain the third row?
I don't know. You mean the third line?
Yeah,
This line?
right above the final answer.
This line?
No, the one below.
This line. So 1 minus T times V naught, just distribute. That's V naught minus T times V naught, right? 1 minus T V naught is 1 times V naught minus T V naught. And then over here, I have plus T V naught. So I just put that here, right? And then this is this, and this is this. But minus T V naught plus T V naught, they cancel. I'm left with just V naught plus the sum of these two vectors. And these are vectors in the subspace W, so this is just some vector, little w, in the subspace W. So I have V naught plus W. That's exactly what my affine subspace is.
And in the first row where it has 1 minus T, is that just what's given?
Yes.
Okay.
That was the problem. To show that this is what's given. This vector, 1 minus T times X plus T times Y, show this belongs to W.
Can you do question 9?
All right, so,
I think we did that one.
yeah, I did that a few
Yeah,
minutes
we
ago.
did that one already.
Oh, okay.
Would you be able to do 20B?
20B. Let's take a look. Ah, okay, so. Twenty B. So we have 3 equations and 3 unknowns. X plus 4y plus 3z equals 1. 2x plus y plus z equal 3. And 3x minus 2y minus z equals 4. So the augmented matrix that corresponds to the system of equations, the first column is 1, 2, 3. The second column is 4, 1 minus 2. The third column is 3, 1 minus 1. And the last column is 1, 3, 4. So if I wrote this down correctly, 1, 4, 3, 1, 2, 1, 1, 3, 3 minus 2 minus 1, 4. And we want to solve the system of equations by putting this matrix in reduced row echelon form. So my first row starts with a 1, which is great. And then I want to get a 0 here. To get a 0 here, I take the second row minus 2 times the first row. So 2 minus 2 is 0. 1 minus 8 is minus 7. 1 minus 6 is minus 5. 3 minus 2 is 1. So I subtracted 2 times the first row from the second. And I want to get a 0 here. So I take the third row minus 3 times the first row. 3 minus 3 is 0. Minus 2 minus 12 is minus 14. Minus 1 minus 9 is minus 10. 4 minus 3 is 1. Okay. And then I want to make this a 1 and zeros above and below. But actually, I notice that minus 7 times 2 is minus 14. So if I take the first row and the second row, if I take the third row minus 2 times the second row, what do I get? I get 0 minus 0, minus 14 plus 14, minus 10 plus 10, 1 minus 2 is minus 1. Now, these matrices are row equivalent. The system of equations corresponding to this is equivalent to the original equation. And what does this last equation say? The last equation says 0x plus 0y plus 0z equals minus 1. Well, that's impossible. There's no solution of this equation. Therefore, this system is inconsistent. If you have to find all solutions, the answer is there is no solution in the universe that solves these equations.
Which question is this again?
Problem 20, part B.
Okay, yeah, we had a question like this in the homework, right?
I hope so. Yeah. I mean, not every system of equations has a solution. Some equations are inconsistent. That means there is no solution. Some equations have a unique solution. Some equations have infinitely many different solutions. It all depends.
Can you do number 18?
Professor, how will you know if there's no solution? How do you figure it out?
Because this equation corresponds to 0 equals -1. That's never true. That means there can't be, if there was a solution, then 0 would equal -1, and it doesn't.
Can I ask you about like another case that's similar to this? What if you give us an equation, a system or a set of equations that don't have enough equations as variables? So let's say you give us an equation with 3 variables, but then you only give us 2 equation statements.
Right?
That's not possible to solve either, right?
No, of course you can solve it. There typically will be infinitely many solutions.
Oh, okay. So we have to like express it as like a system
So
of the other.
you always do the same thing. If you want to use this matrix method, you always write down this augmented matrix, put it in reduced row echelon form, and then you will get either that there's no solution, or there are solutions, and you'll be able to write them down from the reduced row echelon matrix.
Can you do 18 though?
I did that a couple of minutes ago.
Oh, I'm sorry.
I mean, it's being taped, so it'll all be on YouTube a few minutes after the class is over.
Okay, thank you. I have a question about what's going to be on the exam. Will there be questions about Kramer's rule or no?
There could be.
Also, is there like a specific methodology to obtaining the reduced row echelon form, or is it just like you have to kind of figure it out
No,
depending on the coefficients?
there's well, I mean, there is a method, which is you apply the elementary row operations step by step to get the reduced row echelon form, and it's an algorithm. It always works. You know, if this were a computer science class, you could write a computer program for it. So a computer, which has no ability to think, it just follows directions, would do it automatically. That's what an algorithm is. So there is an algorithm. It's you apply elementary row operations, multiply equations by scalars, interchange, multiply rows by scalars, interchange 2 rows, add a multiple of one row to another, and you will always, 100% of the time, get the solution.
Can you do 19B?
$19B is you have the matrix 3, 2, 6, 4. So you want to put this in reduced row echelon form. So I could multiply the first row by a third to get this. Then I can multiply, I want to get a 0 here. So that's the first row. And I multiply the first row by 6 and subtract from the second row, and I get 0, 0. So that's the answer. That's in reduced row echelon form.
Oh, I see, because I tried the problem myself and I got the same result, but I didn't think that was it.
Yeah, no, that's it, because again, in every non-zero row, the first non-zero number is a 1, and in that column, everything else is 0. And any row that's all 0 is below any row which is not all 0. So you can certainly have all 0 rows in your reduced row echelon form, but they have to be at the bottom of the matrix, right? Just the way that is.
Oh, all right. Thank you.
If I interchange the rows 0, 0, 1, 2/3, this is not in reduced row echelon form because the 0, 0 row is at the top, not at the bottom. But this is exactly the answer.
How did you get 0, 0?
Second row minus 6 times the first row. I wanted to get a 0 here. And when I do that, it just happens I get a 0 here as well.
So you did 6 times the first row?
If I take the first row 1, 2/3, if I actually multiply it by minus 6, I get minus 6 minus 4. If I add that to the second row, I get 0, 0.
Okay.
Shouldn't it be -6? Wait. Oh, never mind.
Can we do C, 19C?
Sorry, which one? 19C?
Yeah.
Okay. So I have the matrix 1, 2, 5, 2, 5 minus 1, 3, 1, 0. So the first non-zero entry in the first row is already a 1, so I don't need to change that. To get a 0 here, I take the second row minus 2 times the first row. So 2 minus 2 is 0. 5 minus 4 is 1. Minus 1 minus 10 is minus 11. And then I want to get a 0 here. So I take the third row minus 3 times the first row. So 3 minus 3 is 0. 1 minus 6 is minus 5. 0 minus 15 is minus 15. Right, so now the first non-zero number in the first row is 1, and everything else in that column is 0. Now I look at the second row, and again, I'm lucky. The first non-zero entry is a 1. 0, 1 minus 11, that's what I want. I want to get a 0 here. So I take the first row minus 2 times the second row. So 1 minus 0 is 1. 2 minus 2 is 0. Minus 2 times minus 11 is plus 22. 5 plus 22 is 27. And then I want to get a 0 here. So I multiply the second row by 5 and add to the third row. 0 plus 0 is 0. 5 minus 5 is 0. Minus 55 minus 15 is minus 70. Okay. Now the second column is good. I want this to be a 1. So I have the first row. I have the second row. And the third, I divide by minus 70. I get 0, 0, 1. Then I want to get a 0 here. So if I multiply the third row by 11 and add to the second row, I get 0, 1, 0. And if I add the third row, if I multiply the third row by minus 27 and add to the first row, I get 1, 0, 0. So this is the answer. That's the matrix in reduced row echelon form.
How did you get rid of the -11?
Multiply this row by 11 and add to the second row. Take this row.
And the 27? You
Multiply this row by minus 27 and add to the first row.
Okay.
One more question?
Yes. 10.
Oh, so that's the theorem that I already pointed out in the text. And you have to look it up in the textbook. I could write it out, but it's 4 or 5 or 6 pages to write out. So the purpose of that being on the review is to make you look at the book. But that's a serious theorem to prove. It's section 1.5 in the chapter on linear equations.
Can you tell us about the distribution of problems? Like how many questions will be like computation versus how many like proofs? Like, can
Well,
you tell that? Can you
I have
tell us
no
that?
idea exactly, but roughly speaking, there'll be 12 questions on the exam and you choose 10. So you can leave out 2 that you don't like, and each question is 10 points. So if there's a proof you don't like, skip it. If there's a computational problem you don't like, skip it. But you have some choice.
If I had a if I could do it my way, I'd skip all the proofs, but I don't like, will there be more than 2 proofs?
Well, I haven't made up the exam yet, but I suspect there's going to be at least 1 proof you have to do if you want to get 100. If there are 3 proofs, you can leave them all out, get everything else right, and you still have an A on the exam.
Okay. I mean, that's helpful at least. Thank you.
So, is that implying that there won't be more than 3 proof questions?
Absolutely not.
Okay.
I have no idea. I try and make up an exam that covers all the material in a reasonable way. And once you get to 300 level math classes, there have to be some proofs. Now, linear algebra will have less proofs. Like I'm also teaching a class on number theory. That is much more theoretical. That will have more proofs. Linear algebra will be mostly computational problems, but that's not the same as saying 100% computational problems. And one of the things we hope you learn when you're taking 300 level math classes is how to prove stuff, because mathematics is not just computations, it's proving. So, but in linear algebra, it's much less proofs than in most other 300 level math classes. Also, a lot of people who take linear algebra are in fields like economics or physics, where there's less emphasis on proofs, or even computer science. Though in computer science, there is some kind of proving, but there's a little bit, there are fewer proofs here than in most other 300 level math classes.
I have a question. So you said there's 12 questions, but we only choose 10. Now, if I do like, let's say 11, just to improve my chances of getting a
I
higher.
will grade the first 10 problems and stop.
Okay, that makes, okay.
So pick your favorite 10. Okay, again, let me remind you, we have Zoom sessions, I have problem sessions tonight and tomorrow at 7 o'clock. And if you have questions, I encourage you to log on, because I'm just hanging around. And if no one's there, I go off and eat dinner, but otherwise, I'm around and starting at 7 o'clock. Okay. Bye all. See
Thank
you
you,
in person
Professor.
on Wednesday.
Thank you.